Hi, welcome to the class. We will continue our discussion on origin of spectral lines and also do few numericals based on this. So in the previous class we had discussed this formula which was for hydrogen atom, and this formula was 1 by lambda is equals to r, where r was the Rydberg constant. And if we are putting it for hydrogen, then obviously the value of z will be 1. This will be 1 and it will become just r here because this z will become 1, right? So this is the formula which we will use. Now what happens is when an electron jumps from the lower orbit, let us say this is n1, this is n2, then n3, then n4, n5 and so on. So when an electron jumps from the first orbit to any one of the higher orbits, let us say it is jumping to the fifth orbit. So when it jumps from the first orbit to the fifth orbit, as and when it comes back, so it has multiple options to come back. It may come directly here. So when it comes directly here, this difference is energy is equals to h nu, or this lambda, let us talk about the wavelength or the frequency, right? Because I can write this as hc by lambda. So this wavelength or frequency emitted out by this electron, because this is coming from the higher orbit to the lower orbit. So if it comes directly from fifth orbit to the first orbit, this frequency or the wavelength emitted by the electron will be different from the one when it comes from fifth to fourth, then fourth to third, third to second and second to first. So all these frequencies will differ depending upon the way in which the electron is coming downwards, right? So that is for the downwards. Similarly, when it goes up, the same thing will happen. It might go from first to second, then second to third, third to fourth, fourth to fifth. But it might go from directly from first to fifth, depending on what kind of frequency you're giving or what kind of wavelength you're giving to it, right? So based on that, some spectral series are there, and those spectral series depending on the frequency and wavelength. I'm talking about depending on the frequency and wavelength, and depending on those wavelength and frequency we call them hydrogen spectrum. Now the first hydrogen spectrum which is there is what we call Lyman series, right? So Lyman series, as you could see in that formula, N1 and N2 are there. So when N1 and N2 are there, what happens is, so in the Lyman series, if I talk about the Lyman series, electron jumps from this for Lyman series, Lyman. So I am talking about the Lyman series. Electron is in first orbit and it is jumping to the second, third or fourth. And similarly, if it is at the fourth or third or second, it is coming back to the first one. So it happens in both ways, as while going up also and coming down also. So N1 is equals to 1 for Lyman series and N2 is equals to could be 2, 3, 4, 5, 6. So this if the electron is at the first orbit jumping to second, third, fourth, fifth, sixth, Lyman. If it is at the sixth orbit but coming back to the first orbit, directly if it coming back to the first orbit, then Lyman series. So the formula would be 1 by lambda is equals to r, 1 upon, of course n1 would be 1 and then minus 1 upon n2 square, because this can take multiple values depending on from where it is coming. Now guys, this the wavelength of this Lyman series, you should understand that it lies in the ultraviolet region. This is important. This lies in the ultraviolet region. So this is one important point. Also you should understand that the longest wavelength of this series, would be for n is equals to 2. The longest wavelength for this series would be for n is equals to 2, and the shortest wavelength for this series would be n is equals to infinity. So n is equals to infinity, it will be the shortest wavelength. So if I tell you that we have to calculate it for the shortest wavelength, you will put n2 is equals to infinity. The longest wavelength, you will put n2 is equals to 2, right? So that is Lyman series. Similarly, the next series is what we call Balmer series. Next series is what we call Balmer. So Balmer, you know that N1 will be equal to 2 and N2 will be equal to 3, 4, 5, 6. And if you make the formula, it will be 1 by R. 1 by lambda is equals to R 1 upon 2 square minus 1 upon N2 square. So N2 will range in the value of 3, 4, 5, 6 and so on. Now the Balmer series is in the visible region. This is in the visible region. Visible region. This is one important thing. And the second important thing in this, to keep in mind that the longest wavelength will be for n is equals to 3 and shortest wavelength will be same. So here also shortest wavelength will be n is equals to n2 is equals to infinity, and the longest wavelength would be Balmer series would be n is equals to 3. Now the third series is Paschen series. So in case of Paschen, you know, n1 would be 3 and n2 would be 4, 5, 6 and so on. So again I am telling you it works both ways, while going from third orbit to some other higher orbit, while coming from the higher orbit to the third orbit. Again Paschen series lies in infrared region. So this Paschen series lies in infrared region. Paschen lies in infrared region, and the formula for Paschen series would work like 1 by lambda is equals to R square, 1 by 3 square minus 1 by N2 square. That is Paschen. Next would be bracket. Next would be bracket series. In bracket, N1 would be 4, N2 would be 5, 6, 7 and so on. And this series would lie in the infrared, same as this series. It will also lie in infrared region, and the formula you can easily make it. The last one would be P-Fund series. So P-Fund also lies in infrared region, and you know that here N1 will be 5 for P-Fund and rest of the values you know that, right? So that is there. So these we have discussed about the series. Now how do we solve the problem or the questions related to these things? So let us do some numericals based on this, and all right. So I think this one we have, I don't remember we have done or not, but let us do this question. So in a hydrogen atom, they are saying, they are talking about the hydrogen atom, and they are saying that, I think we have done this, but okay. So they are saying that in a hydrogen atom, an electron jumps from n is equals to 3 to n is equals to 2. So first of all, what you have to do, you have to find out the wavelength. Very first thing is you have to find out the wavelength. Then you have to tell that to which part of the spectral series this particular wavelength will belong, and also you have to tell that whether it will be visible or not, right? So again you can use the formula 1 by lambda is equals to R 1 by N1 square minus 1 by N2 square. Now the value of the R would be, what would be the value of the R? R is 1.097. R is equals to 1.097 into 10 to the power 7 per meter. That would be the value of the R, and rest of the things you can calculate by putting the values. Now in this case you see that it is going from third to second. So basically N1 is equals to what? It is going to second from higher to lower. So N1 is 2. So 2 belongs to 1. What, with which series 2 belongs? Tell me. So it belongs to Balmer. because it is going to second. So as I told you, whether it is going from second to higher orbit or whether it is coming back to the second orbit, it belongs to the Balmer. And in the Balmer region, where does it lie? It lies in the which spectral series is this? I think it lies in the visible region, and if it lies in the visible region, then obviously we will be able to see this. So wavelength, find out the answer for the wavelength. I'll tell you the answer. So lambda would be, you can easily calculate it, I know that. So it would be 6.563 into 10 to the power -7 meter. So this will lie in the visible region and we will be able to see this. So this is the first question. Okay, now let me just find out one more for you so that you can practice. So this is how you have to do it, and yeah. Now this is a question from Bohr's quantization formula. So Bohr's quantization formula is this only, 1 by lambda is equals to r square and all this. What we have to do, determine the largest wavelength in the Balmer series. Largest wavelength in the Balmer series of hydrogen spectrum. Now for largest wavelength in the Balmer series, Balmer is for n is equals to 2. So for largest wavelength, it would be, the value of the n would be n is equals to 3, one more than that. Because in this question they are talking about Balmer series. Now Balmer series starts when n1 is equals to 2. So when n1 is equals to 2, either the electron is coming from the higher orbit to the lower orbit, or it is going from the n1 is equals to 2 orbit to the higher orbit. So Balmer series. So for, they are saying the longest wavelength. So for longest wavelength, in case of Balmer series, n2 will be 3, right? So they are saying determine the wavelength, largest wavelength. They are asking you to calculate for this thing. Determine the largest wavelength. So wavelength would be largest or longest when n2 is equals to 3 and n1 is equals to this. So what formula you will use? R 1 upon n1 square minus 1 upon n2 square. Now put the values and try to solve it. Again the answer would come around to be the same which we had done in the previous, but this was just a variation to show that how does it work, right? And that is how the numericals would come, and this is the end of this chapter, atoms. It brings us to the end of this chapter, atoms, and these questions could be of these types, right? Thank you.